going, and everything looks like it's working. Okay, so today we're going to look at absolute and conditional convergence. Okay, so with absolute convergence, okay, that just says that if the series and that's the series, but of the absolute value of the series. If that absolute value converges, then we know that the series itself converges. And converges absolutely. But with conditional convergence, let's say the series A sub n converges, but the absolute value doesn't. So forgot my sum. Sum of the absolute value diverges. Then the series is conditionally convergent. Excuse me. All right, so let's say, for example, if we wanted to determine if the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 divided by n is convergent or if it diverges, is divergent. Now, if it's convergent, we want to classify it as absolutely or conditionally. Okay, so we decide just to use the alternating series test because we have that -1 to the power of n plus 1. So the alternating series test. Okay, so that first condition is that the limit as n approaches infinity of your a sub n should equal 0 for it to converge. Well, the first condition for it to converge. Well, that's the limit. In this case, your a sub n is 1 over n. If we just get that -1 to the n plus 1 and factor it out to the front. So that's the limit of 1 over n as n approaches infinity. Well, we know that as a constant divided by a number getting bigger and bigger and bigger, that's always going to be 0. So that's first condition is passed. Let's look at the second condition. That's where it's non-decreasing. So in other words, we have our 1 over n, so our a sub n plus 1 is just 1 over n plus 1. It's less than or equal to that 1 over n for all values of n greater than or equal to 1. Okay. Well, this is true. So we know since both conditions are met, it's convergent. At least your a sub n is convergent. Now we have to look at the absolute value of your a sub n. So we take the limit, not the limit, I'm thinking of the wrong test. So we have the sum from n equals 1 to infinity of the absolute value of your a sub n, which is -1 over n plus 1. I'll write that out first. And the reason it's the absolute value is because that -1 to the power of n plus 1 doesn't matter which one it is, it's always going to end up being positive. So that's just the sum from n equals 1 to infinity of the absolute value of that, which is just 1 over n. Well, we could always rewrite that as the sum from n equals 1 to infinity of 1 over n to the first power. And from there, we can just use the p-series test. Remember, that's just the sum from n equals 1 to infinity of 1 over n to the power of p. And we can see here that p is less than or equal to 1. And it diverges. Okay, so we can see that the limit of your series converges, but the absolute value is divergent. So this is conditionally convergent. So we know the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 over n is conditionally convergent. Okay. Both would have to be convergent in order for this to be absolute convergence. Okay. So if the absolute value and the actual series itself converges, then it converges absolutely. But if the absolute value is divergent, then it converges conditionally. All right, anyone still writing? All right. So let's say, for example, if we wanted to determine if the series sum from n equals 1 to infinity of cosine of n times pi divided by 5n squared converges conditionally absolutely, or if it's divergent. Okay. So with this one, you can use any test you want to find out whether or not that series is convergent. So with this one, we're going to use the comparison test. As long as you meet the stipulations for that particular test, you can use whichever one. Okay. First, we're going to look at cosine of n pi. Well, we know cosine of n times pi is always going to be a value between -1 and 1. So it's similar to how you would start the squeeze theorem. So now, since we're looking for cosine of n pi divided by 5n squared, we're going to divide each section by 5n squared. That gives us -1 divided by 5n squared is less than or equal to cosine of n pi divided by 5n squared, which is less than or equal to 1 divided by 5n squared. Okay, so if you remember your compound inequalities, you know the absolute value of x is less than or equal to some value k when x is greater than -k and and less than or equal to positive k. Okay. So we're going to do the same thing, but in reverse. We're going to go and put it in the absolute value form. So this is just equal to the absolute value of cosine of n times pi divided by 5n squared is less than or equal to 1 over 5n squared. Okay, so remember this is 0 is less than a sub n is less than b sub n. Or you can put less than or equal to. So we know if b sub n converges, then your a sub n converges also. Okay. So draw a little arrow. Solve this one on the side. With this one, we're going to use the p-series test. So we see here that our p is equal to 2, which is greater than 1. So we know that, and we can factor out that 1/5, that 1 over n squared converges. Okay. So if this converges, then we know the absolute value converges. Remember, the absolute value, before we apply that, we could have just used this portion here. So we know that this a sub n also converges because this will converge too. Okay, so since this converges, since 1 over 5n squared, converges, we know that the absolute value of cosine of n pi divided by 5n squared converges. Okay. So again, if we did the p-series test right here, we'd get the exact same thing. This converged, so this will also converge. So we know even without the absolute value, it will still converge. So if it converges with and without the absolute value, it converges absolutely. So we know also cosine of n pi divided by 5n squared also converges. So we know the sum from n equals 1 to infinity, cosine of n pi divided by 5n squared converges absolutely. And for me, I just use word association to remember that if it converges with the absolute value, it converges absolutely, with or without the absolute value. But if it only converges without the absolute value, then it does not converge absolutely. All right, any questions on that one? All right, anyone still writing? All right. So let's say if we wanted to determine if the convergent series sum from n equals 1 to infinity of -1 to the power of n plus 1 times n plus 14 factorial divided by n plus 15 factorial converges absolutely. And make that E a little bit neater. Conditionally, or if it diverges. Okay. So with this one, they're letting us know that the series itself converges. Okay. So what we have to do now is just see if the absolute value of the series is also convergent. So if the series and the absolute value of the series both converge, you're good. So with this one, when they tell you the series is convergent, you only have to kind of do half the work. And it's just the absolute value part of it. Okay, so you have the sum from n equals 1 to infinity of the absolute value of -1 to the power of n plus 1 times n plus 14 factorial divided by n plus 15 factorial. And really, you don't have to write it out if you don't want to, because the absolute value, all that does is get rid of that -1 to the power of whatever. Because it doesn't matter what it is, it's still going to be positive. So if you just drop that one, then it's the same thing. So that's the sum from n equals 1 to infinity of n plus 14 factorial divided by n plus 15 factorial. Okay, so with these factorials, we can rewrite it as the sum from n equals 1 to infinity of n plus 14 factorial divided by n plus 15 factorial is just n plus 15 times n plus 14 times n plus 13 plus n plus 12 and keeps on going. So yeah, n plus 15 times n plus 14. And if we kept on going, everything after that would just be n plus 14 factorial. So we see that these two would just cancel each other out. So we have the sum from n equals 1 to infinity of 1 over n plus 15. Okay, but we can't use the p-series test to find out if this is convergent or not, because it has to be just 1 over n to the power of something, and that plus 15 kind of threw that option out the window. So with this one, we can still use the comparison test. Okay, so if we use the comparison test, What if we have 1 over the square root of n? Well, we know that is less than or equal to 1 over n plus 15. Oh, that should be the other way around. Plus 15 is greater than less than or equal to 1 over the square root of n. Where n is greater than or equal to 2. And again, I just plugged in values. That's how I was able to catch that without even thinking about it. Plug in n is equal to 4. Got 1 over 1/17 is less than or equal to 1 half. So So we know that in this case, n is greater than or equal to 2. Okay, so we know here that since this is divergent, because we know from the p-series test, oh, let me check. Yep. That if your p, actually let me rewrite it because that square root should be n to the 1/2 power. So just for visualizing purposes. So instead of pointing at that square root one, let's point at this one. So we can see there that our p is equal to 1/2. Which is less than or equal to 1. So since it's less than or equal to 1, we know it diverges. Okay, so we can see here that the absolute value, so from n equals 1 to infinity of the absolute value of -1 to the power of n plus 1 times n plus 14 factorial divided by n plus 15 factorial diverges. And we know that the sum without the absolute value converges because that was given to us. Okay, so we know that in this case, it's conditionally convergent. So you can just write a sub n, or you can write out the whole thing. I'll write out the whole thing. We know the sum from n equals 1 to infinity of -1 to the power of n plus 1 times n plus 14 factorial divided by n plus 15 factorial converges. Again, that was because it was given to us. So we know that it converges conditionally. Oh, yes.
I thought the tends to 1 over the square root of n is larger than 1 over n plus 15, it diverging won't tell us whether 1 over n plus 15 converges or diverges.
You said I'm sorry, I missed half of that.
Because 1 over the square root of n is larger than 1 over n plus 15, I would have thought that it diverging doesn't tell us anything about 1 over n plus 15.
I see what you're saying. Yep, it does say that. So actually, we couldn't use that test. How did I miss that? Thank you. Yep, because if it diverges, it couldn't tell us. So actually, that was a good catch. Thank you. I don't know, I missed that. But yep, when your B sub n is divergent, it doesn't tell you anything about your A sub n. So we have to get one. Remember, that will take just a couple of seconds. So with this part here, I'm kind of surprised I missed that. I think I must have been preoccupied. So let's look at, let's find one that is divergent. So let's say if we have our 1 over n plus 15, let's make it, trying to think of one that is less than 1 over n plus 15 that we can actually use in that case. So if we have, I'll actually have to rewrite that one. I'm trying to think, why did I miss that one? Obvious. Okay, so what if we let, instead of 1 over square root of n, let's make it, can't be 1 over n because that would give us the same thing. So what if we use, let me see, catch a hint from one of the older ones. It can be 1 over n. Let's see, which one could I use in its place? All right, I'm gonna have to come back to that one, but thank you for pointing that out. Like I said, I have no clue how I missed that one. We're gonna come back to that one only because, like I said, this, you only can prove convergence if your B sub n is greater than your A sub n and your B sub n converges. But if your B sub n diverges, then of course, if that one diverges, it doesn't really say anything about your A sub n. Your A sub n could converge or diverge. With that one, we're going to come to it. So just for this section right here, the answer itself is actually true. But for this section right here, we're going to come back to it. I don't want to burn too much time, because I want to be able to get done with the next section today so you can start on your test. But we'll come back to that one. All right, let me put this over on the side. There we go. Okay, so now we're going to go ahead and start on 9.6. And that's your ratio and root test. And really, the name is exactly how it sounds. Let's look at the ratio test. Okay. So first, we're going to let the series of a sub n have non-zero terms. Or with no non-zero terms. Or with no zero terms. Non-zero terms is no zero terms. Double negative. So with non-zero terms. I was thinking of writing no zero terms or non-zero terms and kind of just melted them together to no non-zero, which is completely opposite to what I was trying to say. So you have non-zero terms. Okay. So first, say that the sum of our series a sub n converges absolutely if the limit as n approaches infinity, or your absolute value of a sub n plus 1 divided by a sub n is less than 1. And the sum of a sub n diverges if the limit as n approaches infinity, so the absolute value of a sub n plus 1 divided by a sub n is greater than 1, or if it equals infinity. Which kind of says the same thing, but I'll write it out anyway. For the third, we keep these kind of similar, so I'll put 1, 2, and 3 there. That the ratio test is inconclusive if the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to 1. And all that means is you have to use a different test. All right, anyone still writing? There we go. Okay, so let's say, for example, find a good example here. Yep, that's a good one. Let's say if we wanted to determine if the sum from n equals 0 to infinity of 2 to the power of n divided by n factorial converge or diverge. Excuse me. Okay, well, for this one, our a sub n will be 2 to the power of n over n factorial. And our a sub n plus 1 is 2 to the power of n plus 1 divided by n plus 1 factorial. Okay, so if we wanted to find our limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, then that would just be the limit as n approaches infinity of the absolute value, and instead of writing it 2n plus 1 divided by n plus 1 and that divided by 2n divided by n factorial vertically, I'll just write it out horizontally. It's 2 to the power of n plus 1 divided by n plus 1 factorial divided by 2 to the power of n divided by n factorial. So you have the limit as n approaches infinity. Using our rules for dividing fractions, we have 2 to the power of n plus 1 divided n plus 1 factorial times, we flip the second one, so we have n factorial divided by 2 to the power of n. Okay, so that gives us the limit as n approaches infinity. So that 2 to the power of n plus 1, we can rewrite that. 2 to the power of n plus 1, we can rewrite that as 2 to the power of n times 2 to the first power, or just 2 times 2 to the power of n. So we rewrite this as 2 to the power of n times 2. Divided by that n plus 1 factorial. We can rewrite that, because remember, that's just n plus 1 minus 1 will be the next factor. So you have n plus 1 times n plus 1 minus 1, which is just n, times n minus 1 times n minus 2, and it keeps on going all the way till you get to 3 times 2 times 1. But we can rewrite this as just n plus 1 times n factorial, because everything from there on down is just n factorial. So that becomes n plus 1 times n factorial. Times our n factorial divided by 2 to the power of n. So we can see here stuff just starts to cancel out. This 2 to the power of n cancels out with this 2 to the power of n. This n factorial cancels out with this n factorial. So that just leaves us with the limit as n approaches infinity of the absolute value of 2 divided by n plus 1. Okay. So when we have the limit of a constant divided by a number getting bigger and bigger, we know that that limit is just equal to 0, which is less than 1. So as long as that limit is less than 1, we know that it converges by the ratio test. All right, any questions on that one? All right. Anyone still writing? All right. Let's say if we wanted to determine if the sum from n equals 0 to infinity of n squared times 2 to the power of n plus 1 divided by 3 to the power of n converges or diverges. Okay, so if we're using the ratio test, then our a sub n is equal to n squared times 2 to the power of n plus 1 divided by 3 to the power of n. Which means that our a sub n plus 1 would be n plus 1 squared times 2 to the power of n plus 1 plus 1. And I could have just said n plus 2, but I'd rather point out the steps. Divided by 3 to the power of n plus 1. Okay, so your a sub n plus 1, we could rewrite that as n plus 1 squared times 2 to the power of n plus 2 divided by 3 to the power of n plus 1. Okay, so if we take our limit as n approaches infinity of the absolute value of our a sub n plus 1 divided by our a sub n, then that's just equal to the limit as n approaches infinity. Your a sub n plus 1, again, I'm just going to write it horizontally. So it's n plus 1 squared times 2 to the power of n plus 2 divided by 3 to the power of n plus 1 divided by your a sub n, which is n squared times 2 to the power of n plus 1 divided by 3 to the power of n. Oops. Okay, so we know that the limit as n approaches infinity, we have n plus 1 squared, and 2 to the power of n plus 2, we can rewrite that as 2 to the power of n times 2 squared. All divided by 3 to the power of n plus 1, we can rewrite that as 3 to the power of n times 3 to the first power, or just 3. If you're dividing fractions, of course, you change division to multiplication, then you can just flip the second fraction. That's 3 to the power of n divided by n squared times 2 to the power of n plus 1. We could just make that 2 to the power of n times 2. And from there, we can start canceling stuff out. We have 3 to the power of n cancels out with that one. This 2 to the power of n cancels out with that one. And this 2 cancels out with one of these two, so we can just make that to the first power. So we can make that the limit as n approaches infinity. The numerator, the only thing left is 2 times n plus 1 squared divided by 3 times n squared. Or we can go ahead and expand that n plus 1 squared. So the limit as n approaches infinity. N plus 1 squared is n squared plus 2n plus 1. N squared plus 2n plus 1 divided by 3n squared. So if we go ahead and distribute that 2, that gives us the limit as n approaches infinity of 2n squared plus 4n plus 2 divided by 3n squared. I'm going to leave a little bit of space under this one. And I did that purposely. Oop, got my closing absolute value. There we go. Okay, so we're going to divide each term by by n squared. So divide each term by n squared, which allows us to simplify this. Or you can multiply by 1 over n squared in the numerator and denominator. Which, same thing. Okay, so this n squared cancels out, and these two n squared cancels out. So that gives us the limit as n approaches infinity of 2 plus 4 over n squared. Well, you can say 4 over n, since that n cancels out. Plus 2 over n squared divided by 3. So if you apply the limit to each term, you know the limit of 2 is just 2. The limit of a constant divided by a number getting bigger and bigger is 0. So that one just becomes 0. Same with a constant divided by a number getting bigger and bigger becomes 0. Divided by the limit of 3, which is 3. So it's the absolute value of 2/3, which is just 2/3, which is less than 1. So since that limit is less than 1, we know that it is convergent. All right, any questions on that one? All right, anyone still writing? All right. Let's say, for example, if we wanted to determine if the sum from n equals 1 to infinity of n to the power of n divided by n factorial converge or diverge. Okay. We know that our a sub n is equal to n to the power of n divided by n factorial. Which means that our a sub n plus 1 is equal to n plus 1 to the power of n plus 1 divided by n plus 1 factorial. of our limit as n approaches infinity of a sub n plus 1 divided by a sub n is equal to, you have the limit as n approaches infinity of your a sub n plus 1. So that's n plus 1 to the power of n plus 1 divided by n plus 1 factorial. Okay. And to kind of save steps, we know it's going to be divided by n to the power of n divided by n factorial, but we're going to change the division to multiplication and flip the second fraction. That's n factorial over n to the power of n. Okay, so that gives us the limit as n approaches infinity. Now we can kind of rewrite these a little bit. So n plus 1 to the power of n plus 1, we can rewrite that as n plus 1 to the power of n times n plus 1 to the first power. We can leave it as just n plus 1. Okay, divided by n plus 1 factorial, well, we can rewrite that as n plus 1 times n factorial, since everything after n plus 1 becomes n factorial. So you have n minus 1, n minus 2, all the way down. Times n factorial divided by n to the power of n. And we can see here that this n plus 1 cancels out with that n plus 1. This n factorial cancels out with that n factorial. So the only thing left is the limit as n approaches infinity of the absolute value of n plus 1 to the power of n divided by n to the power of n. So we have the limit as n approaches infinity. And since they're both raised to the power of n, we can just combine them. And since n is approaching infinity and those are going to be positive no matter what, we can just make it n plus 1 over n to the power of n with parentheses. Okay. And if you plug in values of n, so if you plug in 2, you get 2 plus 1 divided by 2 to the second power, 3 plus 1 divided by 3 to the third power, and keep on going and going and going, we see that that is always going to be greater than 1. Okay. Which we know by the ratio test means it's divergent. Oops, make that E a little bit neater. I have to double check, but I think that's the limit definition of E. 1 plus 1 over n to the power of n. I think that is the limit definition of E. Didn't notice that before. All right, any questions on that one? All right. And I'm actually going to put this aside just to double check if this is the limit definition of E. So we kind of set that aside there. I'll double check after class. All right, so let's say, for example, we wanted to determine the convergence or divergence of the sum from n equals 1 to infinity of -1 to the nth power times the square root of n divided by n plus 1. Okay. Let's say we decided to use the ratio test. We know for your a sub n is equal to square root of n over n plus 1. And your a sub n plus 1 is the square root of n plus 1 divided by n plus 1, which is n plus 2. That means if we take the limit as n approaches infinity of the absolute value of your a sub n plus 1 divided by a sub n, that's just going to equal the limit as n approaches infinity of the absolute value of your a sub n plus 1, which is square root of n plus 1 divided by n plus 2, divided by your a sub n, but it's going to be times its reciprocal, so times the reciprocal of this, which is n plus 1 divided by the square root of n. Now, since multiplication is commutative, we can actually just switch those two with each other. So we have the limit as n approaches infinity of the square root of n plus 1 divided by the square root of n times n plus 1 divided by n plus 2. And let me clean up that square root of n plus 1 a little bit. Square root of n plus 1. There we go. Okay. So of course, since both of those are square roots, we can just combine those and put them as 1. So we can take the square root of n plus 1 divided by the square root of n and just make it the square root of n plus 1 over n. So that takes the limit as n approaches infinity of the absolute value of the square root of the quotient n plus 1 over n times n plus 1 divided by n plus 2. Nope, forgot to close out my absolute value. There we go. Okay, so to simplify each one, you have the limit as n approaches infinity. We're going to divide each one of these terms, well, basically the whole thing, by 1 over square root of n, which just gives us dividing each of these terms by 1 over n, well, 1 over n over 1 over n. So that gives us the square root n divided by n plus 1 over n divided by n divided by n. Times, same thing here, we multiply this by 1 over n over 1 over n. That gives us n divided by n plus 1 divided by n over n divided by n plus 2 divided by n. Okay, these two cancel out to give us 1. These two cancel out to give us 1. These two cancel out to give us 1. And these two cancel out to give us 1. So that gives us the limit as n approaches infinity of the square root of 1 plus 1 over n divided by 1. Or you could just say 1 plus 1 over n. Could have left it like that. Times 1 plus 1 over n divided by 1 plus 1 over n. Or 1 plus 2 over n in that case. So we can see all the ones where you have a constant divided by a number getting bigger and bigger. Those just have a limit of 0. So you can go ahead and cross this out. So that leaves us square root of 1 over 1, which is 1, times 1 over 1, which is 1. So the limit of 1 is just 1. So you can see whenever that limit is equal to 1, it's just inconclusive, which means you just have to use another test. And I'll put it on another sheet instead of trying to squeeze it all in that little bit of space left. All right, anyone still writing? All right. Okay. So the other test we can use the alternating series test. Since we had that negative 1 to the power of n there anyway, probably would have been the best initial choice, but you can always try different ones. Sometimes it'll work, sometimes it won't. Okay, so we know that the first condition, we have to find the limit of your a sub n as n approaches infinity. Where we know that if it equals 0, then it's convergent. So we know that's going to equal the limit as n approaches infinity of your square root of n divided by n plus 1. Okay, so if you take the limit of your numerator, well, the limit of square root of n is just infinity. And the limit of n plus 1 as n approaches infinity is infinity. So we can see here we have an indeterminate form, which means we can use L'Hopital's rule. So that is equal to the limit as n approaches infinity of the derivative of the square root of n, and I'll just write that as n to the 1/2 power just for convenience, divided by the derivative of n plus 1. Well, the derivative of n plus 1 is just 1, so we can kind of ignore that one because whatever derivative we get, it'll be over 1. So that's the limit as n approaches infinity. Bring down the 1/2, so we have 1/2 to the power of, well, times n to the power of negative 1/2. It's 1/2 times n to the 1/2 power. Since the negative 1/2 power, we just move it down. Or you can say square root of n as n approaches infinity. And make that 1/2 a little clearer than that. Two into the 1/2. There we go. So again, we know that whenever you have a constant divided by a number that's getting bigger and bigger and bigger and bigger, that limit is just going to be 0. So it passes the first condition. Now for the second condition, you have to have a sub n plus 1 is less than or equal to a sub n. So it has to be non-decreasing. So if our a sub n is square root of n over n plus 1, that means our square root of n plus 1 is the square root of n plus 1 divided by n plus 1 plus 1, which is n plus 2. Is less than or equal to the square root of n divided by n plus 1. And again, just plug in a few test values. Oh, that's for n greater than or equal to 1. So you can plug in n is equal to 1. That's square root of 2 over 3 is less than 1/2, which is true. And n equals 15. You get square root of 16 over 17. So 4 over 17 is less than 4 over 3, which is true. So as you can see, this is true for all n is greater than or equal to 1. Okay, so we know that this converges. So we couldn't use the ratio test, but we know it converges by the alternating series test. So even though I have my favorites, I like the p-series test because it's nice and easy. It helps to be familiar with the others because you never know when you might need them. All right, any questions on that one? All right. Anyone still writing? Okay. Now we're going to look at the root test. Okay. So we know that the series converges absolutely if the limit as n approaches infinity of the nth root of the absolute value is less than 1. Okay. Or we know that that series converges or diverges if the limit as n approaches infinity of the nth root of the absolute value of your a sub n is greater than 1. Is that or infinity? So you don't have to write the infinity since infinity is greater than 1, but I just like to write it anyway. The limit as n approaches infinity of the nth root base of n is equal to infinity. I know it's kind of redundant, but I just feel better when I write the infinity one. And just like the ratio test, if the root test is equal to 1, it's inconclusive, you'd have to use another method or another test. So the root test is inconclusive if the limit of the nth root as n approaches infinity is equal to 1. And again, we just have to use another test. All right, anyone still writing? All right. So let's say, for example, we want to use the root test to determine if the sum from n equals 1 to infinity of e to the power of 2n divided by n to the power of n converge or diverge. Okay, so we know we have to find the limit as n approaches infinity of the nth root of the absolute value of your a sub n. Well, since n is approaching infinity from 1 to infinity, it's always positive, so we know that these values will also be positive. So if you wanted to, you could drop the absolute value, or you could keep it completely up to you. They have the limit as n approaches infinity of the nth root of e to the power of 2n divided by n to the power of n. Okay. So if we wanted to, you could rewrite this as the limit as n approaches infinity of the nth root. You could say e squared to the power of n divided by n to the power of n. Which is equal to the limit as n approaches infinity of the nth root. So since e squared and n are both raised to the power of n, we can just combine them. You say e squared to the power of n raised to the power of n. Well, we can see here that the index and the exponent cancel each other out. So that gives us the limit as n approaches infinity of e squared divided by n. Okay, so once again, whenever you have a constant divided by a number getting bigger and bigger and bigger, we know that that limit is just equal to 0, which is less than 1. Okay, so we know that by the root test, it converges absolutely. All right, any questions on that one? All right. And I think that was it for chapter 9. Let me double check, but I'm pretty sure that was the last section. Yep, that's the last section. So the test for chapter 9 will be posted shortly. So if you have any questions, of course, feel free to hang back and ask. But since we're having the test for this section, I'm going to go ahead and stop here. So again, if you have any questions, feel free to ask away. If not, I will post the exam and see you tomorrow, and we'll start on chapter 10. So Test should be posted in about 30 minutes. All right, you too. You too, same. All right, you too. So, let's see.
Have a nice day.
All right, you have a nice day too. All right, thank you, Mohammed. You have a good day too. Hey, Donovan, did you have a question?